So up to this point, we've talked about derivatives, we've talked about the chain rule, and we're going to bring those things together, and implicit differentiation, and we're going to bring those things together to talk about what we call related rates. So the idea is this. We know that we have a function, y equals f of x, and when we take the derivative of that function, the derivative of y with respect to x, or derivative of f with respect to x, whatever you want to call it, okay? That's basically measuring the change in y with respect to x, okay? And when you look at this, this numerator is what's changing, and this is what it's changing with respect to. And we've talked about how that relates to slope, velocity, acceleration, all those things. And so we've also seen that with chain rule and implicit differentiation, we can take the derivative of a function implicitly. We can find dy dx implicitly. So this doesn't have to be an explicit function, y equals f of x equals. We can still find dy dx, the change in y with respect to x. And so what we're going to do now is we're going to look at this, and we're going to look at it as it relates to change of variables with respect to another variable, which we'll call time. And so we could find dy dt, the change in y with respect to t being time, or the change in x with respect to t. So we're going to look at an equation that has multiple variables in it, x, y, r, h, whatever the variables are, and we're going to see how those variables, those pieces of this equation, can change with respect to t, time, which will not actually be a variable in the equation itself. So here's an example. We have water is drained out of a conical tank, okay? The volume of that tank with radius r and height h can be described with this v equals 1/3 pi r squared h. So here's your tank. It's filled with water. Now as the water drains, so now it's here and then it's here, we could describe the change in that volume, which is going to be the change in volume over time. But also, if you notice, the radius is changing and the height is changing of where the water is. So we could also see how the radius is changing and how the height is changing, all with respect to time as the water drains over time. And so we can take the derivative of this volume of a cone equation with respect to t and find the related rates of all those variables. And we do it through implicit differentiation. So the idea here would be to start with our equation. V equals 1/3 pi r squared h. We would then take the derivative of this equation on both sides with respect to t this time, not x, t, because we want to see how everything's changing over time with respect to time. So we do that on both sides, which gives us a lot of implicit differentiation, basically all implicit differentiation, because none of these variables in our equation here, here, or here are t. So they're all going to be implicit. Notice 1/3 and pi are constants, in this case constant multiples, so we can handle that as such. And so if we take the derivative with respect to t, well, the derivative of v with respect to t would be dv dt. The 1/3 and the pi can come out. Well, I'll put parenthesis there, parenthesis. Then we have to take the derivative of this with respect to t, but this is a product. So I would take the derivative of the first piece of the product with respect to t, so that would be 2r, then dr dt. I need that dr dt because this variable here and this variable here are not the same, so I'm doing it implicitly. And then product rule says I should then multiply by h plus r squared times the derivative of h with respect to t would be dh dt. And so there is your volume equation as it changes over time, and these are the related rates. The change in v over time, the change in r over time, the change in h over time. All those things, as the water is draining out of this tank, are changing over time. So this would be your related rates equation for the volume of a cone. Now, in order to see how we could use this in an actual problem, rather than just a problem that says describe the related rates, we're basically going to follow these 4 steps. First, identify all the given quantities and quantities that need to be determined from the problem. Possibly make a sketch and label those quantities. It's always a good thing to do when you're reading a word problem. Okay, this is the first step to every word problem, okay, you've ever done in your life. Write an equation involving the variables whose rates of change either are given or are to be determined. So figure out what equation relates all the quantities that you have and need to be determined. Once you have the equation that you know you need to work with, use the chain rule to implicitly differentiate both sides of the equation with respect to t, just like we did. After we complete that step, step 3, substitute in all the resulting equation parts that we know, okay, and then solve for the remaining parts that you want to find. So here's an example of a problem where we can use this related rates. So the air is being pumped into a spherical balloon, okay, so that its volume is increasing at a rate of 100 cubic centimeters per second. Okay, right there, rate at 100 cubic meters per second. That's a derivative they're giving you right there. And that's the volume's derivative. Okay? So just out of that part right there, they're basically telling you that the derivative of V, the change in V over T, is 100 cubic centimeters per second. Okay? Now here's the question. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay? So they're asking you for the change in the radius over time when the diameter is 50 centimeters. Well, we're working with radius, so given us the diameter, we really want to know what the radius is. So radius is just half of the diameter, so this will be 25 centimeters for the radius, so you got to think about that. But this is what we have. We're talking about a sphere. So the formula for a volume of a sphere would be 4/3 pi r cubed. And so if we're going to find this volume, we would have to find the related rates for the variables in this problem. That's both v and r. So if we took the derivative with respect to t of this equation, 4/3 pi would be a constant multiple. So then with derivative with respect to t of r cubed, okay, we would get dv dt equals 4/3 pi times 3r squared dr dt. And this is, again, implicit differentiation. This variable and this variable are not the same, so we take the derivative, so 3r squared, and then we multiply by the derivative of the inside, which is the derivative of r with respect to t. And so we're looking for this. We were given this and this. And so it's just a matter of solving for the variable that we're looking for, dr dt. So let's fill in what we know. We know the change in the volume is 100. We have 3 times r was 25 squared times dr dt. So very simply, these will cancel. 25 squared is going to give you 625. So if we divide that over, we'll have 100 divided by 4 pi times 625 equals dr dt. And we should probably simplify this even more. The 100 and the 4 cancel, we get 25. The 25 and the 625 cancel, giving us 25. And so dr dt would be 1 over 25 pi. 25 pi. And if you wanted to round that, you could say it's roughly 0.0127. And we got to think about units of measurement here. So we were measured in centimeters in second, and this is a change in the radius. So radius is a linear measurement, so that would be centimeters, and it's changing with respect to time, so seconds. So this would be centimeters per second. And so this is how we could describe the change in the volume over time, the change in radius over time. This is how we can figure out how the radius is changing over time with relation to this problem. Here's another one. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? All right. So when you think about this ladder problem, it's basically a right triangle problem. Okay, here's your ladder. Here's your wall. Okay, we know the ladder is 10 feet long. This is the height of the wall. We don't know what the height of the wall is, but this is what's changing, because as the ladder is falling down, this is going out, this is going down, and so that's how this ladder is sliding. Okay, so we have the bottom of the ladder slides away from the wall at a rate of 1 feet per second. So let's call the bottom X and the side Y. So we know the change in X over time, okay, is 1 foot per second. Okay? How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So when this is 6 feet, what's the change in the height? Okay? How fast is the Y value changing? So that's what's happening here with this problem. Now, if we look at this, this would have to be a Pythagorean theorem problem, because we know that x squared plus y squared equals, let's say, the ladder squared, right? But we know that the ladder is always 10 feet. So actually this isn't going to be a variable here, okay? The ladder's length is going to stay the same, so this would be 10 feet squared. Okay? So there's the equation we have to work with. We're going to have to take the derivative of this equation with respect to t, so we can find all the related rates. And remember, this is not changing. This distance is changing, this distance is changing, but this distance is not. So when we take the derivative with respect to t, they're only find a change in x with respect to t and change in y with respect to t, but since this is a constant, that won't be happening. So if we take the derivative with respect to t of both sides of this equation, what do we get? Well, since these are added together, we could take the derivative of each one of these separately with respect to t. Both would be implicit because t is the variable we're taking the derivative with respect to. So this would be 2x, then dx dt, plus the next one would be 2y dy dt. And on the other side, you're taking the derivative of a constant with respect to t, which would be 0. So in order to answer this question, remember, we're looking for the change in y with respect to t, how it's sliding down the wall, and that's the wall, so how's that changing? They gave us the actual length, distance away from the wall, x. They gave us the change in that distance at that particular point in time. What we don't know is y. We got to figure out what that is. And once we have that, then we have everything we need to solve for dy dt. Well, we can figure out what y is, because remember, this is a right triangle. Basically, the ladder is always 10 feet. The specific point in time where we're trying to find the change in the wall's, the height of the wall, this will be 6. the distance away from the wall at the bottom will be 6. So we could figure out what this measurement will be by saying 6 squared plus, say, y squared equals 10 squared. And so you simply do that. It's 100 minus 36. So y equals the square root of 100 minus 36. Okay, and y would give you 8. So we do know y. At this particular point in time where x is 6, the distance away from the base of the wall is 6, this would have to be 8. So filling all that in, we have 2 times 6 times the change in x, which is 1 foot per second, plus 2 times 8 dx, dy dt equals 0. We could then solve for dy dt fairly simply. So this will be 12, move it over, divide by this 16, so dy dt equals negative 12 over 16, which is negative 3/4. And we put a unit of measurement on there. What are we talking about? We're talking about feet per second. So feet per second. This is a linear measurement. We're moving this direction, okay, which is a linear measurement. So it's not like feet squared or feet cubed. It's feet. That distance we measure just in feet. And you see we get a negative answer. Why do we get a negative answer? Because it's falling, because this distance is shrinking, okay? Since this distance is shrinking, it's getting smaller. That's why we got a negative answer here for our dy dt, okay? And notice this distance here, the x distance, is going to get bigger. As this comes down, the ladder is going to slide out this way, so this distance is going to get bigger, which is why that change was measured in a positive value. But anyway, to answer this question, the answer would be the change in y, okay, with respect to t, or the rate at which the ladder is sliding down the wall would be a rate of 3/4 feet per second. Okay? And it's negative because it's changing in a negative direction. It's getting smaller. Here's another one. Pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. Right there. That's a rate. That's a derivative. A derivative of what? The radius. Okay? So right away, what they give us, dr dt is 1 foot per second. When the radius is 4 feet, so the radius is 4 feet, at what rate is the total area of the disturbed water changing? So what's the rate of the area? What's dA dt? Well, we would have to figure out, well, what are we talking about here? We're talking about circles, areas of circles here, okay? And the area of a circle formula would be pi r squared. So if we could take the derivative of this with respect to t, we could see how this area formula is changing over time. So dt of both sides remember that pi is a constant multiple, so that's just going to come out. So we end up with dA dt, that's the derivative of a with respect to t, equals pi times 2r dr dt. So in the question, we're looking for this. They gave us the radius, the specific point in time when we're trying to find the change in the area. They gave us the change in the radius. So fill all that in, and we get dA dt. So dA dt equals 2 pi, r is 4, and the change in r is 1. So what do we get here? We get 8 pi. In terms of units of measurements, area, we're talking about feet and seconds, so feet squared per second. Okay. And you can see that because if you think about this, the radius is measured in feet. The change in the radius over time is measured in feet per second. So if I multiply those together, feet times feet per second, you get feet squared per second. Okay? But also knowing that area is a squared measurement and we're changing with respect to time, time being measured in seconds here, we should be able to come up with that. But anyway, there is your answer, 8 pi feet squared per second. And I like leaving my answer like that. I don't like putting 8 pi into my calculator and getting some decimal answer, because then that's going to have to be rounded. This is the exact rate of change of dA dt. I mean, if it benefits you for some reason to actually multiply 8 times pi and estimate it, you could, but I think the best answer is to leave the exact value of 8 pi feet squared per second. So that's how the area is changing.